This presentation provides a technical overview of the Atlas Wildlife Tracking System. I am Sivan Toledo from the Blavatnik School of Computer Science in Tel Aviv University. I lead the development of Atlas jointly with Ran Natan, the head of the Movement Ecology Lab in the Hebrew University. Atlas tracks wild animals using tracking tags that transmit radio pings, like the white circular tag in the picture. You can see the tracks of the owl on the map on the right, in which each night is shown in a different color. Smaller Atlas tags can track small songbirds, like this reed warbler and this white spectacled bulbul. Atlas can also track bats, like this greater mouse-tailed bat and this Egyptian fruit bat. Here is what Atlas tracking looks like in real time, but accelerated 100 times. The tracks are of bats living in orchard at the end of a night. We have several different types of Atlas tracking tags. They are all tiny and they are inexpensive relative to other kinds of wildlife tracking tags. More than 3,000 Atlas tags have been used so far. Atlas tracking tags are based on the Texas Instruments CC1310 RF microcontroller. They start at less than 1 gram, including battery, antenna, and coating. They transmit about 1 million pings per gram of battery mass. They usually transmit every 1, 2, 4, or 8 seconds, and that can be changed via radio command remotely. They can be put in shipping or deep sleep mode and activated by removing a magnet. We also have optional add-on boards with sensors and flash memory. Virtually all the current Atlas tracking tags transmit on the 434 MHz band, but we also have tags for the 915 and 868 MHz bands. Transmitting tags alone are not sufficient for tracking animals. An Atlas system also consists of receivers or base stations that detect the pings and estimate their arrival times, a server that estimates the location of tags and stores and distributes the data, and clients that monitor the system and visualize and analyze the data. Pings from tags propagate to Atlas base stations. The base stations, whose locations are known, estimate the arrival time of pings. The base stations send the detection reports, which include the estimated arrival times, to the server, which uses these reports to localize the tag. Let us see what Atlas base stations are like. Base stations consist of an antenna and a low noise amplifier, here atop a cellular tower, a filter with a bias T that powers the amplifier, a sampling receiver with a very stable and accurate clock called the GPS disciplined oscillator, and a regular computer running Linux or Windows that performs signal processing on the samples. Base station antennas that are high up improve the range of Atlas base stations and also the accuracy of localizations. This is an Atlas base station in England on top of a wind turbine. Atlas base stations in the shallow Wadden Sea in the Netherlands are placed on scaffolding stuck into the muddy bottom. They are powered by solar panels and small wind turbines. Software in Atlas base stations demodulates the RF signals and also performs precise frequency estimation for phase shift keying tags. It cross-correlates the RF signal with the tag's pseudo-random code to detect pings and to estimate their arrival times. These estimates are subsample estimates. It schedules the signal processing tags. They are executed either on a CPU or on a GPU if there is one. And the base station software also sends these reports to the server, usually at real time, but if the internet connection is down, it queues them in a local database and uploads them later. Now let's see how the Atlas server estimates the location of tags. Atlas is able to localize tags because the unknown location of the tag and the unknown time of departure t are related to the known location of the base station and to the measured arrival time t1 in a particular mathematical way. The expression for the distance between the tag and the base station is given by Pythagoras' theorem. It is the square root of x minus x1 squared plus y minus 1 y1 squared. The time it takes the ping to traverse this distance is the distance divided by the propagation speed, which for radio signals is the speed of light, about 300 million meters per second. We denote this speed by c. We can now relate the times and locations. The arrival time equals the departure time plus the time of travel. Let us see which quantities in this equation we know and which quantities are unknown. We mark known quantities in red and unknown quantities in blue. We know the speed of light and we know the location of the base station. We do not know the time of departure, t, and we do not know the location of the tag. I did not mark t1. We can measure or estimate it, but the measurement is not exact. We address this difficulty by taking t1 to be the measured or estimated time of arrival, not the exact time of arrival, and by adding epsilon1 to the equation to represent the error in the measurement of t1. We clearly cannot resolve x, y, and t from one time of arrival measurement, but we have several base stations. We set up a system of equations, one per base station. The equations describe the arrival times of one ping from one tag. Our aim is to estimate x, y, and t. We cannot estimate the measurement errors epsilon1, epsilon2, epsilon3, and so on because there are too many of them. But if our measurements of the arrival times are accurate, we can assume that the epsilons are small. The server localizes the tag by finding values of x, y, and t that minimize the sum of square of measurement errors. This is called least squares estimation, and that is under some assumptions on the measurement errors. This is justified by the maximum likelihood principle. Users can export tracks from the server's database into files for further processing, but they can also use two types of clients to visualize Atlas tracks directly. A program called Kamadata can connect to an Atlas server and display real-time data. Here we see the track of a bit at real time, along with the table that shows which base stations detect which tags. Kamadata can also visualize tracks from the Atlas database. Here we see tracks of several bits over one night. Users can also view tracks at real time in a web app, which also works on smartphones and tablets. The web app and also Kamadata also display graphs that quantify system health and performance. Finally, let us examine the overall system metrics of Atlas, including performance, accuracy, and throughput. In general, the standard deviations of good localizations is between 1 and 10 meters. There are sometimes outliers with much larger errors. These need to be filtered before the track is analyzed. Atlas annotates each localization with metrics that quantify the error and that can be used to filter outliers. The graphs shown here present data from an experiment to assess the accuracy of Atlas on wild owls. The data indicates that the standard deviation of the localization error is about 5 meters. These tracks from the Waddenzee in the Netherlands show how errors grow when birds get further and further away from base stations. At the center of the coverage area, here in the center of the map, localizations and tracks are very clean and accurate. At the fringes of the coverage area, far away from base stations, tracks become noisy. Three main factors influence the accuracy of Atlas localizations. The first is the signal-to-noise ratio, which is determined by the tag transmit power, usually 10 milliwatts. The ping duration, which is 8 milliseconds, can be made longer or shorter, but we usually use 8 milliseconds. The distance to the base station, usually several kilometers, and also the height of the transmit antenna on the tag and the receive antenna, the base station, the type of antennas, and the quality of the low noise amplifier, and also interference from other transmitters. High bandwidth also helps performance, improves performance. Atlas tags transmit pseudo-random codes at about 1 megabit per second, so they're fairly wideband. The modulation that we use is usually frequency shift keying, but we also have phase shift keying tags that can attain higher performance. And also the number of base stations. This improves performance or influences performance both by averaging and by allowing quality assessment. We need at least 3 base stations to localize, the more the better. Atlas is a stable, high-throughput tracking system. The first system has been running for 5 years, essentially continuously. There are now 5 active systems, the largest one with 26 receivers or base stations. The coverage areas of Atlas systems exceed 1,000 kilometers per system. Users have accumulated more than 900 million localizations in these systems, up to 2.5 million per day per system, and up to 280 million per year per system. Users have tagged over 60 individual animals on one day, multiple times, and that is of course followed by tracking of more than 60 tags simultaneously, and the system can go higher. Tag lifespans range from a few days for small tags to more than 3 months with larger batteries, and the ping rates are 1 Hz to 1/8 Hz. Many of the technical details of Atlas, including many details that have not been covered in this presentation, have been presented in a series of technical papers. Complete citations and links to the papers are available on my website. Papers in which Atlas data is used to draw ecological conclusions are also beginning to appear in the scientific literature. The first two, including a paper in Science, use data from the first Atlas system in the Hula Valley in northern Israel. Additional papers, which use data from additional Atlas systems, should be published soon. Atlas is a collaborative research effort that Ran Natan from the Hebrew University and I lead. Several organizations and many individuals listed on this slide made important contributions to the development of Atlas. Thank you all. Now, if you enjoyed this presentation and you're curious about some of the technical details of Atlas, you may want to check out the technical papers that we published. You may also want to check out my forthcoming book, Location Estimation from the Ground Up, which will be published in September by SIAM. It describes the theory behind Atlas and behind other location estimation systems like GPS, as well as the algorithms that these systems use. Thank you for watching.